Hi, everybody. We are back, and in this segment, we're going to talk about kind of an interesting idea, and that is the difference between, first and foremost, what we refer to as our in-sample error, which we can measure pretty easily because we have sample data, we have a model, and we can compare the model's prediction to the actual values in the sample data. So we can see exactly how much, on average, for example, that the predicted value would deviate from the actual value given our supervised learning setup. So the in-sample error metric, we've talked a little bit about some measures that we can use to calculate this. For example, in linear regression, if you're using the OLS method to recover your parameter estimates, the in-sample error measure that defines our cost function was the sum of the squared residuals, or the sum of squared errors. This is also related to the mean squared error estimate, where we would just divide by the number of observations. We would take our sum of squared errors and we average those out. And it's also related to the root mean square error measurement, where we take the square root of the mean squared error. These are all different ways that you could measure the performance of your predictive algorithm, your predictive model, on the sampled data itself. Now, another idea we've spent some time developing thus far was that there is a difference between learning and memorizing. And unfortunately, we can get very, very good at, quote unquote, having our model memorize the data, in that we use the sample data itself to calibrate the model. Okay, but the problem is we do not have the out of sample data to use to calibrate the model, meaning we're constrained to build the model with the data we have, and we're not really sure ultimately how that model would perform on other observations that we did not include in our sample. So we're going to introduce this idea today of something known as the out of sample error. And the out of sample error is the theoretical error if we were to apply our model to the really the full population of data, okay, which is the out of sample population, which is not included in our sample, right? So with memorizing, it's very easy to create a very complicated model and arbitrarily reduce your in-sample error, this term E in, very easy to push that down to zero. And in this diagram here, you can kind of illustrate this idea that if we think about measuring the complexity of a particular predictive model based off of the number of parameters we have to estimate. For example, in regression, right, if we have k variables, then if we also have an intercept term, we would have k+1 beta parameters to estimate in the case of a linear regression model without any crazy high transformations of the inputs. So we can sort of think in this diagram here of increasing the x-axis value, the number of model parameters. As we increase that, that is really a measure of how complicated the model is, right? The more parameters there are, the more variables the computer needs to solve for when it is solving that cost minimization problem. So in this diagram here, we've illustrated that the number of model parameters increases with complexity along this red locus, this red function that we've drawn here. So the first thing to see here is that increased number of betas, or increased number of model parameters. That means you are dealing with a more complex model that is more flexible to fit all sorts of weird patterns. Okay, the fewer betas you have, the less flexibility you have in trying to actually fit the data. And again, there's a difference between fitting the data versus predicting well. If we fit the data well, what we're actually doing is we are minimizing that in-sample error very effectively. But what we're going to see in a moment is that there is a trade-off. And even though we might be fitting the data well, this is going to be more like memorizing the data that we have. And it turns out when you do that, our performance out of sample, our ability to predict on new observations that we haven't seen yet, at some point can start to suffer from increased model complexity. So there is a trade-off between these two things. You'll notice in the diagram here specifically, it looks like that out of sample error, what we're calling E out, okay, that does reach a point where it minimizes. Okay, so early on with very few parameters, we have a really big out of sample error, but at some level of complexity, we are able to kind of ride this function down to this minimum point here. And that minimum point then would define for us the optimal complexity of our model. How many variables should we have estimated here in terms of determining K star, which in the case of regression, you could think about as the optimal number of betas. Or if you were using a polynomial regression, K would tell you what's the right complexity, the highest order of polynomial to include. So a few things to take away from this picture. Okay, first and foremost, it is possible for us by increasing our model complexity to arbitrarily reduce our in-sample error on the data. Okay, because if we're introducing more complexity, we're making the model more flexible to be able to fit the data. Okay, and unfortunately, after maybe taking a core stats course, you learn a little bit about regression, and you learn about, for example, the R-squared metric, which is a measure of how well your model fits the data. This is a measure of in-sample fit. The R-squared is a measure of in-sample fit of the model. And you may recall that it's easy to make the R-squared go up. You can just keep throwing variables on the other side of the regression. You keep adding regressors. And the R-squared will never go down from adding additional regressors. So it's easy to arbitrarily drive that R-squared up, make that fit better by making a more complex model so that you can reduce your in-sample error arbitrarily low. So this in-sample error function does hit a horizontal asymptote at 0. The other important thing to see here, again, is related to that out-of-sample error function. Okay, and that out-of-sample error function, it reaches some minimum. And that's the important thing about the out-of-sample error function, because if we're interested in actually predicting well on data points we do not see, then being able to identify this minimum is really critical, because it really differentiates the difference between learning well versus memorizing well. Yeah, you can draw a nice, pretty diagram where you fit your data perfectly, but the odds are you're not going to predict well on new observations generated by that same DGP, that data generating process that had given you the sample data originally that you had used to calibrate the model here. So difference between fitting the data well in sample and actually predicting well on that data out of sample. I should say here, I borrowed a couple diagrams from a colleague who teaches a class called Learning from Data at Caltech, Professor Yassir Abu Mustafa. Wonderful course. It talks a lot about these concepts. So if you need another reference, that is a very, very good one. Let's go ahead and talk a little bit more about the difference between our in-sample error and out-of-sample error here. So the out-of-sample error, E out, I'm going to use that here to denote out-of-sample error. The out-of-sample error, if that is very small, okay, that is a sign that your model is a good approximation of the actual process that is generating the data. Okay, and the tricky part about all of this, again, is we don't ever really know what that population function is, what that data generating process is. We can make our best guess at it, but we don't really know what it is. So you're probably thinking, well, how do we measure this out-of-sample error if we can't really observe the data that we don't have, the new data points that we're going to predict from? And we're going to use a little trick later called validation to help us estimate that out-of-sample error by essentially hiding some of our sample from ourselves. So when we build the model, we don't memorize all of the sample data. We use some of it to build the model, but then we can use the data that was hidden from us in order to test that model. If you have a great model, right, a perfect prediction implies that your out-of-sample error would be 0. And this is sort of learning at its best. But in general, the reality is here, and again, when we talk about E in and E out, I'm really referring to the average in and out of sample error. the expectation of this error. But in reality, we expect that the out-of-sample error tends to be larger than the in-sample error. How well we perform on the data that we use to build the model is going to be better than how we tend to perform on new data points that we haven't seen. This is like, if I give you an exam, a practice exam, and you use that practice exam to study. If I gave you that practice exam as the actual test, then I would expect that your performance on that test would be really, really good. You would have a very low in-sample error using that sample exam that I gave you. However, that's not a very good way for me to know that you've learned the material, right? What did you do? Well, you memorized it. The trick is, I want to give you that sample test so you learn the problems well, how to do them, not memorize the answers, and then I give you the actual test, which is different. It's an out-of-sample test. Okay, and whether or not you perform well on those new pieces of information, on that new data, is what's informative in terms of you actually learning. So for us, what we want to think about doing here, given that we can always drive this in-sample error, E-in, we can always make that arbitrarily close to 0, right, by making the model more complicated. Our goal here is to now make sure that we can do everything in our power to try to drive our out-of-sample error closer to this type of bound. Okay, so again, we can always shrink E-in by increasing that model complexity. And we can always shrink that E-in by increasing that model complexity. And again, we're going to do really good at fitting the data. But unfortunately, if we make the model too complex, we're going to see here this actually causes us to force a trade-off where we can make E-in go down, but we're going to make our out-of-sample prediction performance actually get worse, and our out-of-sample error will go up. So there's a couple different perspectives to take on in-sample error and out-of-sample error. If you take the machine learning perspective, you'll hear folks talk a lot about something called the generalization bound or the generalization error, and I'm going to use this Greek letter omega to define that here. And this value omega, what that does is it essentially defines the divergence between our out-of-sample error and our in-sample error. So omega here, what that is doing is it's creating some bound, right, that we add to that E-in, okay, and that is what's constraining our E-out from being low, okay, from being close to E-in, right? If we took this inequality here that I just circled and we were to subtract E-in to the left, we would see the difference between the in-sample and out-of-sample error is described by omega. So in this regard that we wanted to reduce our out-of-sample error performance, we want to improve our performance out-of-sample, learning really implies then that reducing our out-of-sample performance means we should try to reduce the size of that generalization error. Okay, but as I mentioned before, there is a little bit of a dilemma here. Okay, a more complex hypothesis will have a better chance of fitting or approximating F for the given data, okay, which will result in a low in-sample error. But at some level of complexity, we're going to see that despite the fact we can approximate F in the data, we can fit the data well, this does not guarantee that we are going to be actually predicting the data generating process properly. Okay, so there's a little bit of a trade-off here, right? We can make the model more complex and we lower the in-sample fit, but at some point we start driving the out-of-sample error up. And that's really what you care about in terms of predictive analytics and building a model where you're updating that data in real time and making predictions on new observations. On the other hand, a less complex hypothesis is not going to be able to fit the data well, right? If we just had 2 data points, we could fit them perfectly with a straight line, but you throw in a 3rd data point, and now that same complexity of hypothesis is not perfectly capable of fitting that data point, or all 3 rather, unless all 3 data points fell right on that linear regression line. So a less complex hypothesis, you're not going to fit the data as well okay, which is going to result in you sacrificing some in-sample error. However, there may be benefits in reducing complexity in that you may generalize better out of sample. And this is, I think, a very difficult idea to see intuitively here. And there is some mathematics behind it. I'm going to show you it, but it's not a proof I expect you to replicate, but the consequence of the proof is important for us. So the idea here is as follows. It may make sense for us to sacrifice some in-sample error by reducing our model complexity if that means we gain some benefit in actually driving our out-of-sample error down. Okay, and we're going to take a look here at a formal results from statistics. And we're going to start out with a measure of out-of-sample error. Okay, and if you look carefully at this measurement, let me just explain a few elements. So this function g here, that is our hypothesis. Okay, and you'll notice that D superscript, that says G is a function of the data set D. Okay, but it's also a function of our model, which depends on this vector of regressors, or these vector of inputs X. Okay, so this metric that we're looking at here, okay, corresponds to one of the ones that we've seen in an earlier segment. But what are we doing? We're taking the prediction minus the actual value in the data, and we are squaring that deviation. Okay. So it kind of looks like here it's a sum of squared errors. If we divide that by n, we would have a mean square error estimate. And if we took the square root of that, we would have the root mean square error estimate. But point is, we have some sort of cost function in here. And on the outside of that cost function, right, we don't just measure the error on one data point, but we add it up over all of the data points. Okay, so what we're actually doing here is we're taking the average of those deviations with respect to the X variables in our model and with respect to those inputs. Now, what we're going to do in the second line here is we're going to do something kind of strange. Instead of taking the expectation with respect to X, which is exactly what is being done with this term, we're taking the expectation with respect to X, the variables in our model. Okay, we're now going to think about taking the expectation in this next line with respect to not X, but with respect to D, the data itself. And that's kind of a weird thing to think about. What do you mean taking the expectation with respect to the data? Well, remember, our sample data is randomly chosen, provided we are randomly sampling properly. And we know that estimates that we get are sensitive to the sample that we've chosen. So if we had randomly sampled a different set of observations, right, that means our parameter estimates would also be a little different. So the randomness of the parameter estimates is really a function of the randomness in which observations we've included in the sample from the population. So this expectation that we're looking at here in the second line, we're now going to take the average out of sample error, but we're going to think about this average across all of the possible samples of data that we could have generated. And there's a little bit of math involved here. We're going to actually utilize something called the law of iterated expectations. And the linear function of expectations allows us to change the order of expectations here. And what we want to do is evaluate this expression for the out of sample error here. And in order to evaluate this term, okay, and we're going to look at the expectation taken on the inside of this step. So that is exactly what this term is. Okay, and we want to evaluate that thing. To do that, we're going to think about defining something kind of strange also, the average hypothesis. Okay, but it's the average hypothesis not with respect to the X variables, but it's the average hypothesis across the data. So I want you to imagine we built a particular model. Maybe it's a linear regression model with one input and one intercept term. So we got two parameters to estimate. And we have some sample of data. So we get those parameter estimates. We have some optimal hypothesis for that sample. If we had swapped out the data and picked a different random sample, and we use the same model, one intercept and one slope, then we would probably get different optimal values for those two parameters, the intercept and the estimated slope, because there's some sampling error, right? So this expectation here, we're thinking about now our average hypothesis. Okay, averaged over all of the different data sets that we could have included in our sample. So that is what G of X is down here. Okay, we're taking this average, right, over these K different data sets that we could have sampled. Now, the reality is we don't have K different data sets, we got one. But we're gonna think about trying to measure this thing that we can't really access, which is the out of sample error. So what we're gonna do here is we're going to show you that E out decomposes into two important terms here. And again, there's a lot of math. What we do in this step here is we take this quadratic term, we FOIL it, we open it up, and we add and subtract that average hypotheses here so we can now think about errors measured with respect to that. And then we go ahead and we take this outside expectation down through these next steps. And with a little bit of algebra here, we're able to back out some important expressions. We have an expression here that measures how far the hypothesis is for a given data set relative to the average hypothesis squared, and that's what we refer to as the model variance. But then we have another term here which measures how far the average hypothesis is from the actual observations, right? So that's us looking at the wrong point on the target, essentially, and that is what we call bias, which is a systematic problem related to model complexity. That's a problem that the statistical practitioner creates themselves by choosing the wrong model, essentially. But the variance, this first term, that's something that is not really the total fault of the modeler per se here. Now, what you'll notice is through all this math, we're able to decompose the average out of sample error into these two features. We have the bias. Sometimes they refer to that as the bias square, but I'm just going to call it the bias here. And we have the variance. Okay, and as you increase model complexity, it's easy to drive that bias down. A more complex model can fit better. You're going to shoot at that target better. But the problem is increased model complexity tends to drive the variance term up. Okay, so there's a trade-off between those two components. And this trade-off in statistics, a lot of times we'll refer to this as the bias-variance trade-off. So again, our bias term here, this has to do with us not looking at the target. Let me go ahead and clear those drawings. But suppose, you know, the bullseye of the target is over here. Okay, that's the true data generating process, but we're aiming with our hypothesis way over here. Okay, that is the bias. Our hypothesis isn't flexible enough to include the target of the bullseye as an option, so we're systematically off shooting. Okay, the variance, on the other hand, a little bit different. Doesn't have to do with us off shooting. In this case, you'll see there's our bullseye and we're inside. Our hypothesis does include that bullseye, so we're actually looking closer to the right area. But now all the darts we're throwing have a very big spread around where that bullseye is. So all these black dots are us throwing darts and we're missing. We've got a big spread here. I'm going to use this kind of cursive H that you can see here. Right there and right here to denote the hypothesis set. And if you think about now increasing the complexity of the hypothesis itself, right? Meaning we're going to add more parameters to estimate to our model. We're going to increase the complexity. When we do that, it turns out two things happen. We wind up driving the bias down. Okay, but at the same time, we wind up increasing the variance here. So just note that we can see those two effects and how they will influence the out of sample error, right? Lower bias reduces the out of sample error in and of itself, but higher variance is going to push that out of sample error up. So I wanted to kind of wrap up this discussion of the bias variance trade-off momentarily here. By looking at a familiar situation. We had a simulation very similar to this in a homework set question, where we had some function, and the function was specifically a sine function. It was a sinusoid function, an S-shaped function that went up and down. And what we were doing is we were taking this data generating process, the sine function, and we were simulating it, right? Normally we don't know what the DGP is, but we're going to simulate it here. So that is our data generating process in the right diagram. And what we were going to do is we were going to look at sampling a finite sample, just 2 observations from that line, and then compare the performance of 2 different hypotheses. Okay, H0 is a very simple hypothesis. It's just an intercept, a horizontal line, okay, to make our prediction. But H1 is a more complicated hypothesis in that it has a linear component. So now under H1, we're trying to draw the best straight line that can have a slope, but H0 is just the best flat line to fit the data. And the question we're going to think about here is which of these 2 hypotheses performs better? Is it H0 or H1? And again, when we think about performance, we're going to have to differentiate between out of sample and in sample here. So here is the experiment we're going to run. We're taking this the sinusoid function. We're going to sample from it just 2 observations. We're going to build both models with 2 observations. And then we're going to check how do those models perform relative to this actual sine function that I have highlighted here. And it turns out that if you had sampled the entire population function here, if I took every single point on that function and I built both of these models, I built H0 and I built H1, what you would see here is that the theoretical model that performs better in terms of the out of sample error is H1. Okay, H1, we have a 20% out of sample error. H0 though, okay, what is H0? Well, H0 is what's the best flat line to draw to predict, and that best flat line is just right here along the origin. Okay, that is the best prediction of that function if you're constrained to that type of simple hypothesis. But under H1, the best linear hypothesis actually involves a positive slope and a negative intercept term, as you can see here in the diagram. I'm sorry, not negative intercept term. The origin note is actually at the center of this diagram. So there's a 0 intercept term, but there is a positive slope now. So this diagram, both of these diagrams, in fact, are centered at 0 at the origin here. So in theory here, you might be thinking, oh, that that more complex hypothesis looks like it performs better, but the reality is we don't observe the entire DGP. So we're going to now think about the following experiment where we are going to sample, instead of knowing the entire DGP and building the best hypothesis, which is what you're looking at in this diagram, we're instead going to sample 2 data points and then build the best hypothesis, H1, and the constant hypothesis for each case, H0 and H1. So let's suppose that the 2 points that we've sampled here are these 2 points in blue, right? That point and that point. And if we're trying to formulate our best hypothesis where all we can draw is a constant, a horizontal line, then it should make sense that the best hypothesis is going to be just the Y value average of each of those 2 data points. So this green line is more or less right in the middle in terms of the Y values of those 2 data points. That is the best line we can draw to minimize the error on those 2 data points, right? Here's the error on this data point. That's in that direction. Here is the residual on that data point. So that's the best line that we could draw to minimize that residual error there, minimize our cost. Now, if we had sampled the same 2 points, but we now drew the best line which can slope in any direction through those points, hopefully it makes sense that with those same data points, the best linear hypothesis, which has an intercept and a slope term, is able to perfectly fit those data points. And you'll notice I don't even need to draw those red arrows in the right diagram because they fit perfectly. So what we're seeing here is the following situation. Okay, we're seeing that the in-sample error for that simple hypothesis, it's a little bit higher than the in-sample error for the more complicated hypothesis. Right, with only 2 data points, the best linear hypothesis can fit 2 data points perfectly every time. Okay, but remember, Okay, our concern shouldn't really be with the in-sample error if we're trying not to memorize and we're trying to predict out of sample. So imagine we keep doing this procedure. Okay, for each hypothesis, we sample 2 data points, we make the best hypothesis, and then we randomly sample 2 different data points and make the best hypothesis. And we keep doing this over and over and over again. Then what you would witness on the left diagram is you would see a bunch of different hypotheses. Like every one of those gray lines is a different hypothesis corresponding to 2 different samples of data, 2 different data points. Okay, and on the right-hand side, if we were to do this, okay, you would see a bunch of different lines, and the shapes of those lines, again, are dependent on the 2 data points that we had chosen. And remember, every 2 data points, H1 can fit that perfectly in sample. But H0 is not fitting it perfectly in sample here. Okay, H1, every 2 data points, H1 can fit perfectly. So the in-sample error on every hypothesis generated from the data in H1 has a 0 in-sample error, but H0 is a little bit higher. Okay, and it turns out across all of these possible hypotheses, right? This is like us thinking about G bar. What is the best average hypothesis? So if we took all those hypotheses in each diagram, right? We took all these flatline hypotheses in the left diagram. Suppose we averaged them out. Okay, to think about G bar, that average hypothesis. And then we do the same thing over here. Calculate G bar 0 and G bar 1. If we were to do that, what we actually see here is that the average hypothesis for the simpler model does a little bit better. Okay, you'll notice if I add the bias and the variance together, that gives me my measure of E out. So in that left diagram here, okay, we're dealing with a situation where E out is equal to 0.75. And again, the only way we could measure that in this case is because we knew what the population function was. We picked that sign function to simulate to begin with. You'll notice the more complex hypothesis under H1 has a much higher value of E out. Okay, what is it? It is 1.9. Okay, and again, we got that by adding the bias and the variance, right? By taking those expectations over every possible 2-point data set that we could have sampled here. Okay, so the general lesson that I want you to see here is that more complexity in the hypothesis, and this is tempting, right? To throw in all the bells and whistles in your model to try to replicate reality as closely as possible. That's not actually the best thing to do here if you want to make sure you're predicting well and not just memorizing, not having your algorithm perform well on the data that you have, but do a terrible job on the data that you do not have. Okay, so we're going to pick up with this idea in another segment. We're going to look at some learning curves, and we're going to talk about some techniques we can use to kind of tie our hands and protect ourselves from this temptation, or restrain ourselves from this temptation to overly complicate a model. So I hope that was interesting conceptually. We will pick up again with another segment. So I'll see you soon.